Hey there. Imagine waking up tomorrow in a world where sight simply didn't exist. No colors, no shapes, no light piercing through your bedroom window. Just an endless, formless void where touch, sound, and chemical traces are your only guides through life. For nearly 3 billion years, this was reality for every living thing on Earth. But then, in one of the most revolutionary moments in the history of life, something extraordinary happened. The first eyes opened, and the world would never be the same. Tonight we're diving deep into one of evolution's most spectacular innovations. We're talking about the birth of vision itself, the moment when simple light detection transformed into true sight, and how this single breakthrough triggered an evolutionary arms race that would reshape life on our planet forever. So before we begin this journey through ancient seas, take a moment to like this video if you're ready to explore the origins of something you use every second of every day. And let me know in the comments where you're watching from and what fascinates you most about evolution. Now settle in, maybe dim those lights, and let's travel back 540 million years to witness the dawn of sight. Because what we're about to discover isn't just the story of how eyes evolved. It's the story of how vision created predators, transformed ecosystems, and ultimately made complex life as we know it possible. The stage for our story is set during one of the most pivotal periods in Earth's history, the Cambrian period. Picture an alien world, roughly 540 million years ago. The continents are unrecognizable, mostly clustered together in configurations that would seem completely foreign today. The climate is warm and humid with no polar ice caps. Sea levels are dramatically higher than anything we know now, creating vast, shallow seas that stretch across much of what would become modern continents. But here's what makes this period absolutely fascinating. These ancient oceans are about to witness something unprecedented. For billions of years, life had been relatively simple. Sure, there were bacteria, algae, and some basic multicellular organisms, but nothing that would catch your eye if you could somehow snorkel through these primordial waters. Most creatures were soft-bodied, blob-like things that filtered nutrients from water or absorbed chemicals from their environment. The seafloor was covered in microbial mats, essentially living carpets of bacteria that had been Earth's dominant life form for eons. These mats created layered structures called stromatolites, which are actually some of our best evidence for early life. Swimming above these mats were jellyfish-like creatures, some reaching impressive sizes, and various worm-like animals that burrowed through the sediment. But something was stirring in these ancient waters. Evolutionary pressures were building toward a moment that paleontologists call the Cambrian explosion. This wasn't literally an explosion, of course, but rather a relatively rapid diversification of life forms that would unfold over about 25 million years. And at the heart of this biological revolution was one innovation that would change everything: the evolution of complex eyes. Now, you might wonder why eyes were such a game changer. After all, many organisms before this time could detect light. Simple eye spots, basically just clusters of light-sensitive cells, had existed for millions of years. These could tell an organism whether it was in light or shadow, which was useful for things like staying hidden from UV radiation or following daily rhythms. But true vision, the ability to form images and detect shapes, movement, and detail, was something entirely different. This wasn't just about knowing whether it was day or night. This was about seeing food, seeing threats, seeing potential mates, and seeing opportunities. Vision transformed the very nature of survival from a passive process of filtering and waiting into an active game of hunting and hiding. The first creatures to develop sophisticated eyes gained an almost incomprehensible advantage over their sightless neighbors. Imagine being the only person in a room full of blindfolded people. You could move with purpose, avoid obstacles, and achieve goals that others could only stumble toward. This is essentially what happened in the ancient oceans when the first true predators opened their eyes. And leading this visual revolution were some of the most successful animals in Earth's history, the trilobites. These weren't just any arthropods. They were the pioneers of complex vision, the first creatures to see the world in sharp detail, and they would dominate marine ecosystems for nearly 300 million years. Trilobites first appeared in the fossil record about 521 million years ago, right at the beginning of the Cambrian period. But calling them simple early arthropods would be like calling a Ferrari a simple car. These creatures developed some of the most sophisticated optical systems ever discovered in the animal kingdom, and their success story is written in stone across every continent on Earth. Let's start with what made trilobite eyes so revolutionary. Most trilobites had compound eyes, similar to modern insects, but with some crucial differences that made them incredibly advanced for their time. Each eye was composed of hundreds, sometimes thousands, of individual lenses called ommatidia. But here's where it gets really interesting. Trilobite lenses were made of calcite, a crystalline form of calcium carbonate. This might sound like a simple detail, but it's actually extraordinary. Calcite has unique optical properties that trilobites somehow learn to exploit. When light passes through calcite, it splits into two rays due to a phenomenon called birefringence. This would normally create a double image, which would be useless for vision. But trilobites evolved lenses with a precise orientation that eliminated this problem, creating clear, sharp images. Even more remarkable, some trilobite species developed what scientists call doublet lenses. These were essentially compound lenses made of two different materials with different refractive properties. This design corrected for spherical aberration, the same optical problem that telescope makers struggle with today. The fact that trilobites evolved this solution hundreds of millions of years before humans invented corrective lenses is simply mind-boggling. But the sophistication of trilobite vision goes even deeper. Different species evolved eyes adapted to their specific lifestyles and environments. Some had enormous compound eyes with thousands of lenses, giving them incredibly wide fields of view and excellent motion detection. These were likely the visual predators of their time, scanning the water column for prey or threats. Other trilobites developed eyes optimized for different conditions. Some species that lived in deeper waters evolved eyes with fewer but larger lenses, maximizing their ability to gather light in dim conditions. Others that lived on the seafloor had eyes positioned to scan the water above them, perfectly adapted for spotting predators or prey silhouetted against the brighter surface waters. Perhaps most fascinating are the trilobites that lived in the deepest parts of the ocean, where no sunlight penetrated. These species gradually reduced their eyes over evolutionary time, and some became completely blind. Their eye sockets filled in with shell material. This shows us that trilobite vision was not just sophisticated, but also highly adaptable to different environmental pressures. The impact of trilobite vision on Cambrian ecosystems cannot be overstated. These weren't just passive filter feeders or simple scavengers. They were active hunters, capable of tracking down prey with visual precision. Some species developed powerful grasping appendages and crushing mouthparts, becoming the apex predators of their time. But vision created more than just new predators. It sparked an evolutionary arms race that drove innovation throughout the entire ecosystem. When predators could see their prey clearly, prey species had to evolve new defensive strategies. This led to the rapid evolution of shells, spines, armor plating, and behavioral defenses like burrowing and rapid escape responses. The trilobites themselves showcase this arms race beautifully. Some species evolved elaborate spines and defensive structures, suggesting they were both predators and prey in these complex food webs. Others developed the ability to roll up into tight balls when threatened, protecting their soft undersides behind their hard exoskeletons. This visual revolution also transformed how organisms found mates and recognized members of their own species. For the first time in Earth's history, creatures could use visual signals for communication. Some trilobites developed elaborate eye structures and body ornamentations that may have served as species recognition signals or even sexual displays. The success of trilobites as visual pioneers is evident in their incredible diversity and longevity. Over their 300 million year reign, they evolved into more than 20,000 known species, adapting to virtually every marine environment on Earth. They ranged in size from tiny species, smaller than a pill bug, to giants over 2 feet long. They occupied ecological niches as predators, scavengers, filter feeders, and burrowers. What makes trilobite eyes even more remarkable is that they represent just one solution to the challenge of vision. During this same period, other animal groups were independently evolving their own optical systems. The ancestors of vertebrates were developing camera eyes similar to our own. Cnidarians were experimenting with simple lenses and mirrors. Even some single-celled organisms were creating sophisticated light-focusing structures. This parallel evolution of vision across multiple lineages tells us something profound about the advantages that sight provides. When the same complex adaptation evolves independently in different groups, it's a strong signal that this trait offers enormous survival benefits. The fact that eyes evolved dozens of times throughout the history of life demonstrates just how transformative vision can be. But the story of early vision isn't just about trilobites, remarkable as they were. The Cambrian seas were filled with other pioneering visual predators, each developing their own unique approaches to the challenge of sight. Some of these early experiments in vision were so unusual that they seem almost alien to our modern understanding of how eyes should work. Consider Opabania, a bizarre five-eyed predator that cruised the Cambrian seafloors. This creature had 5 mushroom-shaped eyes arranged along the top of its head, giving it an almost 360-degree field of view. Its most distinctive feature was a long, flexible proboscis tipped with a grasping claw, which it used to snatch prey that it spotted with its multiple eyes. Then there was Anomalocaris, perhaps the most formidable predator of its time. Growing up to 6 feet long, this creature had enormous compound eyes that could be over 3 inches in diameter. These massive visual organs gave Anomalocaris incredible visual acuity, allowing it to hunt effectively in the 3-dimensional environment of the open ocean. What made these early visual predators so successful wasn't just their ability to see, but how they used that vision to completely transform hunting strategies. Before eyes evolved, predation was largely a matter of chance encounters or chemical detection. A predator might stumble upon prey or follow chemical trails through the water, but the hunt was slow, inefficient, and often unsuccessful. Vision changed everything. For the first time in Earth's history, predators could actively search for, track, and pursue their prey with deadly precision. They could spot movement from a distance, judge the size and speed of potential targets, and coordinate complex attack behaviors. This wasn't just an improvement in hunting efficiency. It was a complete revolution in how life interacted. The evidence for this transformation is written in the fossil record itself. Before the Cambrian period, fossils show us creatures with soft bodies and relatively simple lifestyles. But as soon as complex eyes appeared, we see an explosion of defensive innovations. Shells became thicker and more elaborate. Spines grew longer and sharper. Burrowing behaviors became more sophisticated, with creatures digging deeper and more complex tunnel systems. This wasn't coincidence. This was evolution responding to the sudden appearance of visual predators. When your enemies could see you clearly, hiding became a matter of life and death. The pressure to avoid being eaten drove rapid innovations in defense, camouflage, and escape strategies. But perhaps the most fascinating aspect of this visual arms race was how it drove the evolution of intelligence itself. When survival depends on outmaneuvering creatures that can see you, simple reflexes aren't enough. You need to be able to process visual information quickly, make split-second decisions, and coordinate complex behaviors. Trilobites, despite being arthropods, developed surprisingly sophisticated nervous systems. Their brains, while simple by modern standards, were far more complex than anything that had existed before. They needed neural circuits capable of processing information from thousands of individual lenses, integrating that data into coherent images, and translating visual input into coordinated movement and behavior. This neural complexity extended beyond just processing vision. Trilobites developed behaviors that suggest they could learn, remember, and even engage in basic problem solving. Some species formed complex trails on the seafloor, following leaders in organized processions that may have been migration routes or feeding expeditions. Others showed evidence of social behaviors, gathering in groups during molting periods when they were most vulnerable. The sophistication of trilobite behavior becomes even more impressive when we consider the environmental challenges they faced. The Cambrian oceans weren't the calm, stable environments we might imagine. Sea levels fluctuated dramatically. Ocean chemistry changed as atmospheric oxygen levels rose. Volcanic activity created localized extinction events. Climate shifts altered current patterns and nutrient distribution. Through all of these changes, trilobites not only survived, but thrived. Their visual systems allowed them to adapt quickly to new conditions, find new food sources, and avoid emerging threats. When other creatures were struggling to cope with environmental changes, trilobites were using their eyes to spot new opportunities and exploit them. The diversity of trilobite eye designs tells us just how flexible and adaptable vision can be as an evolutionary solution. Some species developed eyes that could rotate independently, like chameleons, giving them the ability to track multiple targets simultaneously. Others evolved eyes on stalks that could be extended or retracted, allowing them to peer over obstacles or hide their visual organs when threatened. Perhaps most remarkably, some trilobites developed specialized visual systems for specific tasks. Certain species evolved eyes with different zones optimized for different functions, with some areas specialized for detecting motion, while others were designed for high-resolution detail work. This kind of sophisticated optical engineering wouldn't be seen again until much later in evolutionary history. The success of these visual innovations is evident in trilobite distribution patterns. These creatures colonized virtually every marine environment on Earth, from tropical shallow seas to deep ocean basins, from polar regions to equatorial zones. Wherever there was water, there were trilobites, using their remarkable eyes to carve out ecological niches and dominate local ecosystems. But trilobites weren't the only creatures revolutionizing vision during this period. The Cambrian seas were filled with experimental approaches to sight, many of which seem almost science-fictional by modern standards. Some creatures developed mirror-based eyes that used reflective surfaces to focus light, similar to reflecting telescopes. Others experimented with scanning eyes that moved continuously to build up images over time. One particularly intriguing group developed what paleontologists call neural superposition eyes. These complex optical systems use sophisticated neural processing to combine information from multiple lenses, creating images with resolution and sensitivity that far exceeded what any individual lens could achieve. The computational requirements for this kind of vision processing suggest these early creatures had remarkably advanced nervous systems. The impact of these visual innovations extended far beyond individual species' success. The evolution of complex eyes fundamentally altered the structure of marine ecosystems. Food webs became more complex and interconnected. Energy flow patterns changed as visual predators became more efficient hunters. Behavioral complexity increased throughout entire communities as species adapted to living in a world where being seen could mean death. This transformation is what paleontologists call the Great Ordovician biodiversification event, a massive increase in species diversity that followed closely on the heels of the Cambrian explosion. The two events are intimately connected, with the evolution of vision driving much of the subsequent diversification as species adapted to the new reality of visual predation and visual communication. The chemical signature of this transformation is preserved in ancient rock formations. Isotope ratios in Cambrian limestone show dramatic changes in ocean productivity and nutrient cycling, consistent with the evolution of more efficient predation. Trace fossil evidence reveals increasingly complex burrow systems and defensive structures. Even the mineral composition of shells and exoskeletons changed as creatures invested more energy in protective armor. What makes this period particularly fascinating for scientists is how quickly these changes occurred in geological terms. While 25 million years might seem like an eternity from a human perspective, it's incredibly rapid for major evolutionary innovations. The evolution of complex eyes and the subsequent ecosystem transformations happened in what amounts to a geological instant. This rapid pace suggests that once vision evolved past a certain threshold of complexity, it created powerful feedback loops that accelerated further innovation. Better eyes led to more successful predators. More successful predators created stronger selection pressure for better defenses and escape strategies. Better defenses drove the evolution of even more sophisticated eyes and hunting techniques. The result was a biological arms race that pushed both predators and prey to ever greater levels of complexity and sophistication. The simple, blob-like creatures of the pre-Cambrian world were replaced by an incredible diversity of animals with complex behaviors, sophisticated sensory systems, and intricate ecological relationships. Modern studies of trilobite fossils continue to reveal new insights into just how advanced these early visual systems were. High-resolution scanning techniques have shown that some trilobite lenses were arranged in precise mathematical patterns that optimized light-gathering efficiency. Others had internal structures that suggest they could detect polarized light, giving them enhanced contrast vision and possibly even navigation capabilities. Perhaps most remarkably, some trilobite species appear to have had color vision. Microscopic analysis of their eye structures reveals specialized cells that could have been sensitive to different wavelengths of light. If confirmed, this would mean that these ancient arthropods were seeing their world in vivid color more than 500 million years ago, adding an entirely new dimension to their sensory experience and behavioral complexity. The story of early vision isn't just about the past, though. Understanding how these first complex eyes evolved provides crucial insights into the fundamental principles of perception and consciousness. The neural processing required for vision is incredibly sophisticated, involving real-time analysis of massive amounts of sensory data, pattern recognition, and predictive modeling of movement and behavior. The fact that creatures with relatively simple brains could accomplish this kind of sophisticated information processing suggests that the computational principles underlying vision are more fundamental than we might have imagined. The solutions that trilobites evolved to the challenges of visual perception may have laid the groundwork for all subsequent advances in nervous system complexity and cognitive ability. System complexity and cognitive ability. The evolutionary leap from simple light detection to complex vision represents one of the most profound transformations in the history of life on Earth. But to truly understand the magnitude of this change, we need to examine exactly how these first sophisticated eyes actually worked, and more importantly, how they gave their owners such a devastating advantage over everything else swimming in those ancient seas. When we look at the fossilized remains of early Cambrian creatures, what strikes paleontologists most is the sudden appearance of what can only be described as biological precision instruments. These weren't crude experiments in sight. These were sophisticated optical systems that in many cases rival or exceed the performance of modern animal eyes. Take the compound eyes of trilobites, for instance. Each individual lens, or ommatidium, was precisely shaped and positioned to maximize light gathering while minimizing optical distortion. The surface of each lens was curved according to mathematical principles that humans wouldn't formally discover until the development of advanced optics centuries later. The spacing between lenses followed patterns that optimized resolution while preventing interference between adjacent visual units. But here's where it gets truly remarkable. Recent analysis of trilobite eye fossils using advanced imaging techniques has revealed that these creatures didn't just stumble upon good vision through random mutations. They evolved multiple sophisticated solutions to complex optical problems that modern engineers still struggle with. Consider the challenge of underwater vision. Water absorbs and scatters light differently than air, creating unique optical challenges. Colors fade with depth, contrast decreases, and the angle of incoming light changes constantly due to wave action and current movement. Modern submarine periscope designers spend millions of dollars trying to solve these same problems. Trilobites solved them 500 million years ago, using nothing but evolutionary trial and error. Different species developed eye structures specifically adapted to their depth preferences and hunting styles. Shallow water species evolved eyes optimized for high contrast and color discrimination. Deep water hunters developed enlarged lenses and specialized light-gathering structures that could detect the faintest traces of bioluminescence or reflected light from the surface. Some of the most sophisticated trilobite eyes belong to species that lived in the mid-water column, that twilight zone where surface light begins to fade but hasn't completely disappeared. These creatures evolved what scientists call superposition compound eyes, where multiple lenses work together to focus light onto single photoreceptor cells. This design dramatically increases light sensitivity while maintaining sharp image resolution. The mathematical precision required for this type of optical system is staggering. Each lens must be positioned and oriented with incredible accuracy. The photoreceptor cells must be arranged in precise patterns. The neural circuitry that processes the incoming visual information must be capable of integrating data from hundreds or thousands of individual optical units into coherent, useful images. And trilobites weren't just building these systems, they were constantly improving them. The fossil record shows a clear evolutionary progression in eye complexity and sophistication throughout the Cambrian period. Early trilobite species had relatively simple compound eyes with basic light detection capabilities. But as predation pressure increased and ecological niches became more specialized, their visual systems evolved rapidly in response. By the Middle Cambrian, some trilobite species had developed eye structures that paleontologists describe as almost impossibly sophisticated. Certain species evolved lenses with internal structures that could focus different wavelengths of light at different depths, essentially creating primitive chromatic aberration correction. Others developed specialized eye regions with different optical properties, allowing them to simultaneously optimize for different visual tasks. The neural processing power required to handle input from these complex visual systems would have been enormous by the standards of early animal evolution. Trilobite brains, while still relatively simple compared to modern arthropods, show clear evidence of specialized visual processing regions. These creatures were dedicating significant portions of their nervous systems to the task of seeing and interpreting their visual world. But the revolution in vision wasn't limited to compound eyes. During this same period, other animal lineages were experimenting with completely different approaches to the challenge of sight. Some early vertebrates were developing camera eyes, single lens systems similar to our own that could produce sharp, focused images across their entire visual field. The advantages of camera eyes are different from those of compound eyes, but equally impressive. While compound eyes excel at detecting movement and provide wide fields of view, camera eyes can achieve much higher resolution and are better suited for detailed examination of objects. The choice between these two optical strategies would have profound implications for the hunting and survival strategies of early visual predators. Camera eyes require different neural processing strategies than compound eyes. Instead of integrating information from thousands of individual visual units, camera eyes must process complex images as unified wholes. This requires sophisticated pattern recognition abilities and the capacity to extract meaningful information from detailed visual scenes. The early vertebrates that evolved camera eyes were essentially developing the foundation for all subsequent advances in vertebrate vision, including eventually our own visual systems. The basic architecture of the camera eye, with its cornea, lens, and retina, was established during this period and has remained essentially unchanged for over 500 million years. What makes this period even more fascinating is that we can see evidence of direct competition between different visual strategies. In some Cambrian fossil assemblages, we find camera-eyed and compound-eyed predators living side by side, each exploiting slightly different ecological niches based on their visual capabilities. Compound-eyed arthropods tended to dominate open water environments where motion detection and wide visual fields provided the greatest advantages. Camera-eyed vertebrates were more successful in complex environments with lots of visual obstacles, where high resolution and detailed pattern recognition were more important than wide-angle surveillance. This ecological partitioning, based on visual capabilities, represents one of the earliest examples of what biologists call adaptive radiation. Different visual strategies allowed related species to exploit different resources and habitats, reducing direct competition and allowing multiple lineages to coexist and diversify. The success of these early visual predators is written clearly in the fossil record. Cambrian rock formations show a dramatic increase in the diversity of predatory species, accompanied by equally dramatic changes in prey species morphology. Shells became thicker and more complex. Spines grew longer and more elaborate. Behavioral defenses like burrowing became more sophisticated and widespread. But perhaps the most telling evidence for the impact of early vision comes from the trace fossils, the preserved tracks and burrows that show us how these ancient creatures actually behaved. Pre-Cambrian trace fossils are relatively simple, showing mostly random wandering patterns consistent with creatures searching for food through chemical cues or chance encounters. Cambrian trace fossils tell a completely different story. We see evidence of directed movement, pursuit patterns, and complex three-dimensional behaviors that could only be accomplished by creatures with sophisticated sensory capabilities. Some trackways show clear predator-prey interactions, with pursuing trails that follow and respond to the movements of fleeing prey. These behavioral traces reveal just how fundamentally vision transformed the nature of life in ancient oceans. The random, largely passive existence of pre-Cambrian creatures was replaced by an active, dynamic world of hunters and hunted, where survival depended on the ability to see and respond to threats and opportunities. The arms race between visual predators and their prey drove innovations that extended far beyond simple defensive structures. Some prey species evolved complex camouflage patterns, becoming masters of disguise in their attempts to avoid visual detection. Others developed warning coloration, bright patterns that advertised their toxicity or unpalatability to potential predators. Still others evolved behavioral strategies that took advantage of the limitations of early visual systems. Some species became primarily active during twilight hours when light conditions made visual hunting more difficult. Others learned to use environmental features like coral reefs or algal mats to break up their silhouettes and avoid detection. The sophistication of these anti-predator strategies tells us something important about the visual capabilities of Cambrian predators. Effective camouflage and warning coloration only evolve in response to predators with relatively sophisticated vision. Simple light detection wouldn't create the selection pressure necessary to drive the evolution of complex visual deception strategies. This suggests that by the Middle Cambrian period, visual predators had already achieved remarkable levels of optical sophistication. They could distinguish shapes, patterns, and colors well enough to make camouflage and warning displays evolutionarily advantageous for their prey. The diversity of visual strategies that evolved during this period is truly staggering. Some predators specialized in detecting movement against static backgrounds, developing visual systems optimized for motion detection at the expense of fine detail resolution. Others evolved high acuity vision that allowed them to spot camouflaged prey or identify specific target species in complex visual environments. Certain species develop specialized visual hunting strategies that seem almost alien by modern standards. Some early arthropods evolved eyes with different optical properties in different regions, essentially creating biological zoom lenses that could switch between wide-angle surveillance and high-magnification detail work. Others developed what paleontologists call scanning vision, where the eyes moved constantly to build up detailed images of their environment over time. This strategy allowed creatures with relatively simple optical systems to achieve remarkable visual performance through behavioral adaptations. The energy costs of maintaining these sophisticated visual systems must have been enormous. Eyes are metabolically expensive organs, requiring constant maintenance and consuming significant amounts of energy during operation. The fact that so many different lineages independently evolved complex vision during this period suggests that the survival advantages must have been absolutely overwhelming. Modern studies of arthropod metabolism show that compound eyes can consume up to 20% of an animal's total energy budget. For Cambrian creatures living in environments where food was often scarce and competition was intense, this represents an enormous investment. The fact that they made this investment tells us just how crucial vision had become for survival. The success of early visual predators also created new opportunities for other types of organisms. As predation became more efficient and widespread, it created ecological niches for scavengers that could exploit the remains of predation events. It also created opportunities for smaller organisms that could hide in the spaces between predators and prey, essentially becoming the first cleaner species. The complexity of Cambrian ecosystems increased dramatically as these new ecological relationships developed. Food webs became more interconnected and hierarchical. Energy flow patterns became more efficient as visual predators reduced the amount of energy tied up in slow-moving, inactive prey species. This ecological transformation had profound effects on ocean chemistry and nutrient cycling. More efficient predation meant faster turnover of organic matter and more rapid recycling of essential nutrients. The chemical signatures of this change are preserved in Cambrian rock formations, showing clear evidence of increased biological productivity and more complex biogeochemical cycles. The evolution of vision also had unexpected effects on the development of social behaviors and communication systems. For the first time in Earth's history, organisms could use visual signals to communicate with members of their own species. This opened up entirely new possibilities for coordination, cooperation, and mate selection. Some Cambrian arthropods show evidence of visual display structures that may have been used for species recognition or sexual selection. Elaborate spines, colorful patterns, and specialized eye arrangements all suggest that these creatures were using vision not just for hunting and avoiding predators, but for communicating with each other. The implications of visual communication for early animal societies cannot be overstated. The ability to recognize individuals, coordinate group behaviors, and engage in complex social interactions all depend on sophisticated visual processing capabilities. The evolution of these abilities during the Cambrian period laid the groundwork for all subsequent advances in animal social behavior. As we examine the fossil evidence from this revolutionary period, what becomes clear is that the evolution of complex vision wasn't just another incremental advance in animal capabilities. It was a transformative event that fundamentally altered the trajectory of life on Earth. The world that emerged from the Cambrian explosion was unrecognizably different from what came before, and vision was the key innovation that made it all possible. The creatures that first opened their eyes in those ancient seas couldn't have known that they were initiating one of the most important transitions in the history of life. But their evolutionary innovation would echo through time, influencing every subsequent chapter in the story of complex life on our planet. The arms race they started continues today, driving the evolution of ever more sophisticated visual systems and the complex behaviors that depend on them. From the compound eyes of trilobites to the camera eyes of early vertebrates, from the mirror eyes of deep-sea creatures to the scanning systems of primitive arthropods, the Cambrian period established all the basic principles of vision that continue to guide evolution today. Every time you open your eyes and see the world around you, you're using systems and principles that were first developed by creatures swimming in ancient seas over 500 million years ago. 1 billion years ago. But the story of early vision extends far beyond the success of individual predators. What happened next fundamentally changed how life itself operated on our planet. As these first visual hunters began to dominate ancient seas, they set off a cascade of evolutionary pressures that would reshape every aspect of marine ecosystems. The transformation wasn't gradual. Geological evidence suggests that within just a few million years of complex eyes appearing, marine communities underwent what paleontologists call ecological restructuring. The simple, mat-covered seafloors of the pre-Cambrian world were suddenly filled with creatures digging elaborate burrows, constructing defensive shells, and engaging in behaviors that would have been impossible without sophisticated sensory systems guiding them. Consider what happened to the ancient seafloor itself. For billions of years, bacterial mats had dominated shallow marine environments, creating layered structures that preserved a record of microbial life. But as visual predators began actively hunting through these environments, the mats were disrupted, churned up, and eventually largely destroyed by the constant activity of creatures that could see where they were going and what they were doing. This disruption, known as the agronomic revolution, represents one of the most dramatic ecological transitions in Earth's history. The static, layered world of microbial mats was replaced by a dynamic, three-dimensional ecosystem where creatures moved with purpose, burrowed with precision, and interacted in ways that had never existed before. The fossil record from this period reveals an explosion of burrowing behaviors that could only have been accomplished by creatures with visual guidance. Complex tunnel systems appear suddenly in Cambrian rocks, showing evidence of sophisticated engineering that required the ability to navigate three-dimensional spaces and construct elaborate underground networks. Some of these burrow systems are remarkably advanced, with multiple chambers, specialized areas for different functions, and complex branching patterns that suggest their builders could visualize and plan their construction projects. This kind of spatial reasoning and forward planning represents a level of cognitive sophistication that was previously unknown in animal evolution. The ability to see also transformed how creatures moved through their environment. Pre-Cambrian trace fossils show mostly random wandering patterns, consistent with organisms searching for food or suitable habitat through chemical cues alone. But Cambrian trackways tell a completely different story. We see evidence of directed movement, complex navigation patterns, and coordinated group behaviors that required sophisticated sensory integration. Some of the most remarkable trace fossils from this period show what paleontologists call pursuit and evasion patterns. These trackways preserve actual predator-prey chases in stone, showing how visual predators tracked and pursued their targets, while prey species attempted to escape using evasive maneuvers that would have been impossible without their own visual systems to guide them. The sophistication of these behavioral traces suggests that by the Middle Cambrian period, marine ecosystems had developed complex predator-prey dynamics comparable to modern ocean communities. This represents an incredible acceleration in evolutionary complexity, achieved in a fraction of the time it had taken life to reach even basic multicellularity. But vision didn't just create more efficient predators and more evasive prey. It also enabled entirely new forms of ecological relationships. For the first time in Earth's history, organisms could engage in visual communication, opening up possibilities for cooperation, social behavior, and complex mating systems. Some Cambrian arthropods show evidence of visual display structures that appear to have served no function other than communication with other members of their species. Elaborate eye stalks, colourful body patterns, and specialised appendages all suggest that these ancient creatures were using sight not just for survival, but for social interaction. The implications of this development are profound. Visual communication allowed for the evolution of complex social structures, coordinated group behaviours, and sophisticated mating systems. These innovations laid the groundwork for all subsequent advances in animal social behaviour, from insect colonies to vertebrate societies. The metabolic costs of maintaining sophisticated visual systems were enormous, but the evolutionary benefits clearly outweighed these expenses. Modern calculations suggest that the compound eyes of large Cambrian arthropods could have consumed up to 30% of their total energy budget. This represents one of the largest single investments in sensory capability in the history of animal evolution. The fact that so many different lineages independently made this massive energetic investment tells us something crucial about the advantages that vision provided. In the competitive environment of Cambrian seas, the ability to see clearly was literally a matter of life and death. This period also saw the evolution of what biologists call sensory arms races, where improvements in predator vision drove corresponding advances in prey sensory systems, which in turn selected for even better predator capabilities. The result was a feedback loop that rapidly pushed both hunters and hunted toward ever greater levels of sensory sophistication. Some prey species evolved their own visual systems specifically adapted for predator detection. These anti-predator eyes were often quite different from the hunting eyes of their predators, optimized for wide-angle surveillance and motion detection rather than high-resolution image formation. Others developed non-visual sensory systems to complement or compensate for their visual limitations. Enhanced chemical detection, vibration sensing, and even primitive echolocation systems all appear in the fossil record during this period, suggesting that the pressure from visual predators was driving innovation across all sensory modalities. The diversity of solutions to the challenge of avoiding visual predators is truly remarkable. Some creatures evolved elaborate camouflage systems, developing body patterns and textures that made them nearly invisible against their preferred backgrounds. Others adopted warning coloration strategies, advertising their toxicity or unpalatability through bright, conspicuous patterns. Still others evolved behavioral adaptations that exploited the limitations of early visual systems. Nocturnal activity patterns became common among prey species, taking advantage of low-light conditions when visual hunting was more difficult. Rapid escape responses evolved in multiple lineages, allowing prey to outmaneuver predators even after being detected. The sophistication of these anti-predator adaptations provides important clues about the visual capabilities of Cambrian predators. Effective camouflage and warning displays only evolve in response to predators with relatively advanced color vision and pattern recognition abilities. The fact that these strategies were so widespread during the Cambrian suggests that visual predators had already achieved remarkable levels of optical performance. Recent studies of Cambrian fossil assemblages have revealed evidence for complex ecological networks that rival those of modern marine ecosystems. Food webs from this period show multiple trophic levels, specialized feeding relationships, and intricate patterns of resource use that could only have been maintained by organisms with sophisticated sensory capabilities. The energy flow patterns in these ancient ecosystems were fundamentally different from anything that had existed before. Visual predators were far more efficient hunters than their predecessors, capturing and consuming prey at rates that dramatically increased the turnover of organic matter and nutrients. This increased efficiency had cascading effects throughout entire ecosystems. Primary productivity increased as nutrients were recycled more rapidly. Biodiversity expanded as more efficient energy transfer supported larger numbers of species at higher trophic levels. Ecosystem stability improved as complex food webs provided multiple pathways for energy and nutrient flow. The chemical signatures of these changes are preserved in Cambrian rock formations around the world. Isotope ratios in ancient limestone show clear evidence of increased biological productivity and more complex biogeochemical cycles. Trace element compositions reveal changes in ocean chemistry consistent with more efficient biological processing of nutrients. Even the mineral composition of shells and exoskeletons changed during this period, as organisms invested increasing amounts of energy and resources in protective structures. The appearance of biomineralization on a massive scale during the Cambrian was largely driven by the need to defend against visual predators that could target vulnerable soft-bodied prey with deadly precision. The evolution of complex biomineralization represents another major innovation that was directly linked to the rise of visual predation. Creatures needed protection from predators that could see them clearly and target their most vulnerable areas. Simple soft tissues were no longer adequate defense against hunters that could coordinate precise attacks. The variety of defensive strategies that evolved during this period is staggering. Some organisms developed thick, heavily mineralized shells that could resist crushing attacks. Others evolved elaborate spine systems that made them difficult to handle or swallow. Still others developed segmented armor that allowed them to roll into protective balls when threatened. These defensive innovations, in turn, drove the evolution of more sophisticated predatory strategies. Visual hunters developed specialized feeding appendages capable of breaking through shells, prying apart armor, and extracting prey from protective structures. The constant escalation between offense and defense created a powerful engine for evolutionary innovation. The impact of this arms race extended far beyond the immediate participants. As predators and prey evolved increasingly sophisticated capabilities, they created new ecological opportunities for other organisms. Scavengers could exploit the remains of predation events. Parasites could take advantage of the complex life cycles and behaviors of their hosts. Symbiotic relationships developed between species that could benefit from each other's specialized capabilities. The three-dimensional complexity of Cambrian ecosystems was unprecedented in the history of life. For the first time, marine environments were fully utilized from the seafloor to the water surface, with different species occupying specialized niches at every depth and in every microhabitat. This vertical stratification of ecosystems was largely made possible by the evolution of vision. Creatures could navigate precisely through three-dimensional space, target resources at specific depths, and avoid competition by occupying distinct vertical zones. The result was a dramatic increase in the total number of species that could coexist in any given area. The behavioral complexity that emerged during this period is equally impressive. Cambrian creatures engaged in sophisticated hunting strategies, elaborate escape behaviors, and complex social interactions that required advanced cognitive capabilities. The neural processing power needed to coordinate these behaviors represents a major advance in the evolution of animal intelligence. Some of the most remarkable evidence for this cognitive sophistication comes from the trace fossils themselves. Certain trackway patterns show clear evidence of learning and memory, with individual organisms modifying their behavior based on previous experiences. Others reveal complex decision-making processes where creatures evaluated multiple options before choosing specific courses of action. The evolution of advanced cognition during the Cambrian period established the foundation for all subsequent developments in animal intelligence. The basic neural architectures for processing complex sensory information, making decisions, and coordinating behaviors were all established during this revolutionary period in Earth's history. Modern neuroscience research has shown that the fundamental principles of visual processing are remarkably conserved across different animal lineages. The same basic strategies for detecting edges, recognizing patterns, and tracking movement that evolved in Cambrian arthropods are still used by insects, vertebrates, and other animals today. This conservation of visual processing mechanisms suggests that the solutions developed during the Cambrian period were so effective that they have remained essentially unchanged for over 500 million years. The basic toolkit for vision that emerged from this evolutionary experiment has proven robust enough to support the entire subsequent history of complex animal life. The global impact of the Cambrian visual revolution extended far beyond individual ecosystems. As visual predators spread throughout the world's oceans, they carried their innovations with them, rapidly transforming marine communities on every continent. The fossil record shows remarkably similar patterns of diversification and ecological change in Cambrian deposits from around the globe. This worldwide transformation represents one of the most significant biological events in Earth's history. In the span of just a few million years, the entire character of life on our planet was fundamentally altered by the evolution of complex vision. The simple, largely static world of the Precambrian was replaced by a dynamic, competitive environment that would set the stage for all subsequent evolutionary developments. The success of early visual predators also had important implications for the evolution of intelligence and consciousness. The neural processing requirements for sophisticated vision pushed early animals toward greater cognitive complexity, establishing the foundation for advanced behaviors, learning, and eventually, awareness of their environment. As we examine the remarkable fossil record of this period, what becomes clear is that the evolution of vision was far more than just another sensory innovation. It was a transformative event that accelerated the pace of evolution itself, creating new selection pressures, new ecological opportunities, and new possibilities for biological complexity. The creatures that first developed sophisticated eyes in the Cambrian seas initiated changes that continue to reverberate through evolutionary history today. Every predator-prey interaction, every complex behavior, every advanced cognitive ability can trace its origins back to that pivotal moment when the first compound eyes opened in ancient oceans and fundamentally changed what it meant to be alive on planet Earth. The ripple effects of the Cambrian visual revolution extended far beyond the immediate success of individual predators and prey. What emerged from this period was something unprecedented in the history of life. The first truly complex ecosystems, where dozens of species interacted through intricate webs of predation, competition, and cooperation. But to understand just how revolutionary this transformation was, we need to examine what scientists call the Great Ordovician Biodiversification Event, which followed directly on the heels of the Cambrian explosion. This wasn't just another wave of species diversification. It was the direct consequence of visual predators pushing ecological complexity to entirely new levels. The fossil record from early Ordovician deposits, roughly 485 million years ago, tells a remarkable story. Marine communities that had been dominated by relatively simple assemblages of trilobites, early mollusks, and primitive echinoderms suddenly exploded into incredibly diverse ecosystems with hundreds of interacting species. What made this diversification so extraordinary was its speed and scope. Within just 10 million years, marine biodiversity increased by over 400%. New ecological niches appeared faster than they could be filled. Evolutionary innovations spread rapidly through populations as species adapted to the new competitive landscape created by visual predation. The driving force behind this diversification was what ecologists call niche partitioning. As visual predators became more efficient hunters, they created intense competition among prey species for safe refuges and unexploited resources. This pressure forced different species to specialize in increasingly narrow ecological roles, allowing many more species to coexist in the same geographic areas. Some of the most fascinating examples of this specialization come from the brachiopod communities of the early Ordovician. Before visual predation became widespread, most brachiopods were relatively similar, filter-feeding creatures that lived attached to the seafloor. But as predation pressure increased, they rapidly diversified into dozens of distinct forms. Some species evolved thick, heavily ribbed shells that were difficult for predators to crush. Others developed elongated shapes that could burrow partially into sediment for protection. Still others evolved specialized attachment strategies that allowed them to colonize previously unused surfaces, like the undersides of rocks or the walls of crevices. This kind of rapid adaptive radiation was happening simultaneously across multiple groups of organisms. Trilobites themselves were diversifying into an incredible array of forms, each adapted to specific visual hunting strategies or defensive requirements. Some species developed enormous compound eyes for life in the open ocean. Others reduced their eyes and specialized in burrowing lifestyles where vision was less important. Perhaps most remarkably, some trilobite lineages evolved what paleontologists call schizochral eyes, compound visual systems of unprecedented sophistication. Each lens in these eyes was individually shaped and positioned with mathematical precision, creating optical instruments that could resolve fine details while maintaining wide fields of view. The neural processing requirements for these advanced visual systems were staggering. Calculations based on the number and arrangement of lenses suggest that some trilobite species were dedicating over half their nervous system capacity to visual processing. This represents one of the most extreme sensory specializations in the entire fossil record. But trilobites weren't the only creatures pushing the boundaries of visual performance. During this same period, early cephalopods were evolving camera eyes that rivaled those of modern squid and octopuses. These ancestral nautiloids developed sophisticated lenses, adjustable pupils, and complex retinal structures that allowed for incredibly detailed vision. The success of these visual innovations is evident in cephalopod diversification patterns. From a handful of simple species in the early Cambrian, cephalopods exploded into hundreds of different forms during the Ordovician. Some grew to enormous sizes, becoming the apex predators of their time. Others specialized in hunting specific types of prey or exploiting particular depth zones. One of the most impressive examples is Camaracaris, a straight-shelled cephalopod that could reach lengths of over 30 feet. This massive predator used its advanced visual system to hunt large prey in the open ocean, representing the first truly gigantic visual predator in Earth's history. The ecological impact of these giant visual hunters was profound. Their presence fundamentally altered the structure of marine food webs, creating new selective pressures that drove innovation throughout entire ecosystems. Smaller organisms were forced to develop better hiding strategies, faster escape responses, and more sophisticated defensive behaviors. The arms race between these early visual predators and their prey led to some of the most remarkable defensive innovations in the fossil record. Some organisms developed complex camouflage systems that could fool sophisticated visual predators. Others evolved warning coloration strategies, advertising their toxicity through bright patterns that visual hunters learned to avoid. Perhaps most impressively, some prey species evolved their own advanced visual systems specifically for predator detection. These anti-predator eyes were often quite different from hunting eyes, optimized for detecting movement and changes in light patterns rather than forming detailed images. The co-evolution of predator and prey visual systems created feedback loops that accelerated innovation on both sides of the relationship. As predators developed better vision, prey evolved more sophisticated evasion strategies. As prey became harder to catch, predators evolved even more advanced hunting techniques. This evolutionary arms race had cascading effects throughout entire ecosystems. The increased efficiency of visual predation meant that energy moved through food webs more rapidly. Nutrients were recycled faster. Biological productivity increased. The overall complexity and stability of marine ecosystems reached levels that had never existed before. The chemical signatures of these changes are preserved in rock formations from around the world. Isotope ratios in Ordovician limestone show clear evidence of more complex carbon and nitrogen cycling. Trace element patterns reveal changes in ocean chemistry consistent with increased biological activity and more sophisticated ecological processes. Even the physical structure of marine environments was transformed by the activities of visual creatures. Complex three-dimensional reefs began to appear, built by organisms that could see where they were growing and coordinate their construction activities. These biological structures created new microhabitats that supported even greater species diversity. The evolution of reef ecosystems represents one of the most important ecological innovations of this period. For the first time in Earth's history, organisms were actively constructing complex three-dimensional habitats that provided shelter and resources for hundreds of other species. These early reefs were quite different from modern coral reefs, but they served similar ecological functions. They were built primarily by organisms called stromatoporoids, primitive sponge-like creatures that could apparently coordinate their growth patterns to create complex architectural structures. The ability to construct these elaborate biological buildings required sophisticated sensory capabilities and behavioral coordination. Individual organisms had to be able to assess their local environment, communicate with their neighbors, and modify their growth patterns to contribute to the overall structure. Recent research has revealed that some of these early reef builders had simple visual systems that allowed them to orient their growth toward optimal light conditions and coordinate with adjacent organisms. This represents one of the earliest examples of collective construction behavior guided by sensory feedback. The three-dimensional complexity of these reef environments created ecological opportunities that had never existed before. Hundreds of species evolved to exploit the nooks, crannies, and specialized microhabitats within these biological cities. The result was an explosion of biodiversity that transformed shallow marine environments around the world. The success of early reef ecosystems also demonstrates the importance of visual communication in the evolution of complex animal societies. Many of the organisms living in these communities appear to have used visual signals to coordinate their behaviors, recognize species identity, and mediate competitive interactions. Some of the most remarkable evidence for early visual communication comes from trace fossils showing complex social behaviors. Certain trackway patterns reveal coordinated movement by groups of organisms, suggesting they could use visual cues to maintain formation and coordinate their activities. Other trace fossils show evidence of territorial behaviors, with individual organisms apparently defending specific areas from competitors. This kind of spatial behavior would have been impossible without sophisticated visual systems to recognize boundaries and monitor the activities of rivals. The evolution of territorial behavior represents a major advance in animal cognition and social organization. It requires the ability to remember spatial relationships, recognize individual competitors, and make complex decisions about when to fight or flee. These cognitive capabilities laid the foundation for all subsequent advances in animal social behavior. The basic neural architectures for processing social information, making strategic decisions, and coordinating group activities all have their origins in the visual innovations of the early Paleozoic period. Modern studies of animal behavior have shown that many of the social strategies that evolved during this period are still used by contemporary species. The same basic principles of territorial defense, group coordination, and visual communication that emerged in ancient seas continue to govern animal societies today. The global impact of these early visual innovations cannot be overstated. As sophisticated visual systems spread throughout the world's oceans, they transformed marine ecosystems on every continent. The fossil record shows remarkably similar patterns of ecological change in deposits from North America, Europe, Asia, and Australia. This worldwide transformation represents one of the most significant biological revolutions in Earth's history. Within the span of just 20 million years, the entire character of marine life was fundamentally altered by the evolution and refinement of complex vision. The creatures that pioneered these visual innovations were essentially conducting a massive evolutionary experiment. They were testing the limits of what biological optical systems could achieve and exploring the ecological possibilities that sophisticated vision could create. The results of this experiment established the foundation for all subsequent evolution of complex life. The basic principles of predator-prey interactions, the fundamental structures of ecological communities, and the essential neural mechanisms for processing sensory information were all established during this remarkable period. As we examine the fossil evidence from these ancient seas, what emerges is a picture of life undergoing rapid, fundamental transformation. The simple, largely predictable world of early multicellular organisms was replaced by dynamic, competitive ecosystems, where success depended on the ability to see clearly, move quickly, and think strategically. The visual revolution that began with the first compound eyes of trilobites had grown into something far more profound. It had become the driving force behind the evolution of intelligence, consciousness, and complex behavior. The ability to see had evolved from a simple sensory capability into the foundation for all the sophisticated cognitive abilities that would eventually make complex animal societies possible. But perhaps most remarkably, this transformation was still accelerating. The innovations of the Ordovician period were just the beginning of an evolutionary process that would continue to push the boundaries of what biological systems could achieve. The visual systems that had emerged from these ancient seas would continue to evolve, becoming more sophisticated and more powerful with each passing geological age. The story of early vision is ultimately the story of life itself, discovering new possibilities. When the first creatures opened their eyes in Cambrian seas, they initiated a process of discovery and innovation that continues today. Every time a modern animal uses its vision to hunt, to hide, to communicate, or to navigate, it is participating in an evolutionary experiment that began over 500 million years ago. The legacy of those first visual pioneers lives on in every eye that sees, every behavior that depends on sight, and every cognitive process that transforms raw sensory data into understanding and action. They didn't just evolve the ability to see, they evolved the foundation for awareness itself, setting the stage for all the remarkable developments in animal intelligence and consciousness that would follow in the hundreds of millions of years to come. The profound changes triggered by early vision didn't stop with the reorganization of marine ecosystems. As these visual innovations continued to spread and evolve, they began to influence the very chemistry of the oceans themselves, creating feedback loops between biological evolution and planetary processes that would reshape Earth's entire biosphere. One of the most significant of these changes was what geochemists call the Great Ordovician Biodiversification Event's chemical signature. As visual predators became more efficient hunters and prey species evolved more sophisticated defensive strategies, the rate of biological activity in the oceans increased dramatically. This wasn't just about more species existing. It was about those species processing materials and energy at unprecedented rates. The evidence for this acceleration is written in the chemical composition of rocks laid down during this period. Isotope ratios of carbon, nitrogen, and sulfur all show dramatic shifts that indicate much more rapid cycling of these essential elements through biological systems. What had once been relatively slow, steady processes became dynamic, rapidly fluctuating cycles driven by the intense biological activity of visually guided ecosystems. Perhaps most remarkably, the evolution of complex vision appears to have influenced ocean oxygen levels themselves. As visual predators became more efficient hunters, They increase the turnover rate of organic matter in marine environments. Dead organisms were consumed more quickly, organic waste was processed more efficiently, and the overall productivity of marine ecosystems increased substantially. This increased biological activity had a direct impact on ocean chemistry. More efficient decomposition meant that less organic carbon was buried in seafloor sediments, which in turn affected the global carbon cycle. The result was a complex series of feedback loops between biological evolution and atmospheric chemistry that influenced climate patterns worldwide. The fossil record from this period reveals another fascinating consequence of the visual revolution: the emergence of what paleontologists call ecological engineering. For the first time in Earth's history, organisms were actively modifying their environments on a large scale through visually guided behaviors. The most dramatic examples of this come from the trace fossil record, which shows increasingly complex bioturbation patterns as creatures with sophisticated visual systems began to actively reshape seafloor environments. Instead of the simple, random burrow systems of earlier periods, we see evidence of planned construction projects that required three-dimensional spatial reasoning and coordinated effort. Some of these bioturbation patterns are remarkably sophisticated, showing evidence of creatures that could visualize complex underground architectures and execute construction projects that spanned multiple generations. Certain burrow systems from this period show clear evidence of maintenance and modification over time, suggesting that their builders could remember and return to specific locations to continue their work. The ability to engage in this kind of environmental modification represents a major cognitive advance. It requires not just the ability to see and navigate through three-dimensional space, but also the capacity for planning, memory, and abstract thinking about spatial relationships. These cognitive capabilities had profound implications for the evolution of animal intelligence. The neural processing requirements for coordinated construction behavior pushed early animals toward greater brain complexity and more sophisticated behavioral repertoires. The foundation for all subsequent advances in animal cognition was being established by creatures that needed to see, remember, and plan in order to survive. But the visual revolution wasn't limited to marine environments. As sophisticated visual systems proved their worth in the oceans, evolutionary pressure began building for similar innovations in other habitats. The late Ordovician period saw the first tentative steps toward the colonization of terrestrial environments, and vision played a crucial role in making this transition possible. The earliest land colonizers faced challenges that were completely different from those encountered in marine environments. Air is much less dense than water, which changes the physics of locomotion and sensory perception. Light behaves differently in air, creating new optical challenges and opportunities. The three-dimensional structure of terrestrial environments is far more complex than that of most marine habitats. Successfully navigating these challenges required sensory systems that could function effectively in both aquatic and terrestrial environments. The compound eyes that had proven so successful for marine arthropods needed to be modified to work in air. Camera eyes required adjustments to function effectively in the very different optical environment above water. The fossil record shows clear evidence of these adaptations occurring during the late Ordovician and early Silurian periods. Early terrestrial arthropods show modifications to their visual systems that improved their performance in air. Some species developed specialized eye structures that could function effectively in both water and air, allowing them to exploit resources in intertidal and marginal environments. These transitional visual systems represent some of the most sophisticated optical engineering in the entire fossil record. Creating eyes that could function effectively in two completely different optical environments required solutions to complex problems in physics and neurobiology that modern engineers still struggle with. The success of these early terrestrial colonizers established the foundation for all subsequent evolution of land-based ecosystems. The visual systems that allowed the first arthropods to see clearly on land would eventually give rise to the complex terrestrial food webs that dominate modern ecosystems. Meanwhile, back in the oceans, the visual arms race was continuing to drive innovation at an accelerating pace. By the Middle Ordovician period, some marine predators had evolved visual systems that approached the theoretical limits of what compound eyes could achieve. The mathematical precision required for these optical instruments rivals that of modern telescope design. Recent analysis of exceptionally well-preserved trilobite eyes has revealed optical innovations that seem almost impossibly sophisticated for creatures that lived over 450 million years ago. Some species developed aspherical lens surfaces that corrected for multiple types of optical aberrations simultaneously. Others evolved graded index lenses that focused different wavelengths of light at precisely the same focal plane. The neural processing requirements for these advanced visual systems would have been enormous. Computer modeling suggests that some trilobite species were dedicating up to 60% of their total nervous system capacity to visual processing. This represents one of the most extreme sensory specializations ever documented in the fossil record. But this investment in sophisticated vision was clearly worthwhile. Trilobites with advanced visual systems show evidence of complex hunting behaviors, elaborate social interactions, and sophisticated navigation abilities that would have been impossible with simpler sensory equipment. Some of the most remarkable evidence for advanced trilobite behavior comes from mass mortality assemblages, fossil deposits that preserve the remains of hundreds or thousands of individuals that died simultaneously. These deposits show clear evidence of coordinated group behaviors, including what appear to be migration events and spawning aggregations. The ability to coordinate the movements of thousands of individuals across vast distances requires sophisticated communication and navigation systems. The fact that trilobites could accomplish this kind of coordination demonstrates just how advanced their sensory and cognitive capabilities had become. The success of these group behaviors also reveals something important about the social complexity that had evolved in early marine ecosystems. These weren't just collections of individuals competing for resources. They were organized societies with complex behavioral repertoires and sophisticated communication systems. The evolution of social behavior in early marine arthropods established many of the basic principles that continue to govern animal societies today. The use of visual signals for coordination, the ability to recognize and respond to group identity markers, and the capacity for collective decision-making all have their origins in these ancient marine communities. Modern studies of arthropod social behavior have shown remarkable similarities between the strategies used by contemporary species and those that can be inferred from the fossil record of their ancient relatives. This suggests that the fundamental principles of social organization were established very early in the evolution of complex visual systems. The global impact of these early social innovations was profound. As visually guided group behaviors spread throughout marine ecosystems, they created new forms of ecological interaction that had never existed before. Coordinated hunting, collective defense, and group migration all became important factors in ecosystem dynamics. These social behaviors also had important implications for the evolution of intelligence and consciousness. The cognitive requirements for successful participation in group activities pushed individual organisms toward greater neural complexity and more sophisticated behavioral capabilities. The feedback between individual cognitive evolution and group social complexity created powerful evolutionary pressures that accelerated the development of advanced nervous systems. The brains that emerged from this process were not just more complex than their predecessors, they were qualitatively different, capable of processing social information and coordinating complex behaviors in ways that had never existed before. This period also saw the emergence of what paleontologists call behavioral traditions, consistent patterns of behavior that were passed from generation to generation within populations. Some trilobite species show evidence of traditional migration routes that were used repeatedly over thousands of years. Others appear to have maintained traditional feeding grounds and spawning areas across multiple generations. The ability to maintain behavioral traditions requires sophisticated memory systems and social learning capabilities. Individuals must be able to learn complex behaviors from their elders and pass that information on to their offspring. This represents a major advance in the evolution of animal cognition and social organization. The development of behavioral traditions also had important implications for ecosystem stability and resilience. Populations that maintained consistent behavioral patterns were better able to exploit resources efficiently and respond effectively to environmental changes. This created more stable and predictable ecosystem dynamics that could support greater species diversity. As these various innovations accumulated and interacted, the character of marine life continued to evolve at an unprecedented pace. By the late Ordovician period, ocean ecosystems had achieved levels of complexity and sophistication that would not be out of place in modern marine environments. The three-dimensional structure of these ancient ecosystems was remarkably similar to that of contemporary marine communities. Different species occupied distinct vertical zones in the water column, each adapted to specific light conditions, pressure regimes, and resource availability. Complex food webs linked organisms across multiple trophic levels, creating stable and resilient ecological networks. Perhaps most remarkably, these ancient ecosystems showed clear evidence of what ecologists call keystone species effects. Certain visual predators had such profound impacts on community structure that their presence or absence could dramatically alter the composition and behavior of entire assemblages. The recognition of keystone species effects in ancient ecosystems represents an important advance in our understanding of how ecological communities function. It demonstrates that the complex interdependencies that characterize modern ecosystems were already well established over 450 million years ago. The study of these ancient keystone species also provides important insights into the role of vision in ecosystem organization. Many of the most influential keystone species from this period were visual predators whose hunting behaviors created cascading effects throughout entire food webs. The removal or addition of these key visual predators could trigger rapid reorganization of entire communities, demonstrating just how central vision had become to the functioning of marine ecosystems. The ability to see clearly was not just an individual advantage, it was a community organizing force that shaped the structure and dynamics of entire biological systems. As we examine the remarkable fossil record from this period, what becomes clear is that the evolution of complex vision had triggered changes that extended far beyond the immediate success of individual species. The visual innovations that began with simple compound eyes in trilobites had grown into a comprehensive transformation of life on Earth. The oceans that emerged from this period of rapid evolution were fundamentally different from anything that had existed before. They were more diverse, more complex, more dynamic, and more interconnected than previous marine ecosystems. The simple, largely static communities of the pre-Cambrian world had been replaced by intricate biological networks that pulsed with activity and innovation. But perhaps most importantly, these ancient ecosystems had established the basic template for all subsequent evolution of complex life. The principles of predator-prey interaction, the mechanisms of ecosystem organization, and the foundations of animal intelligence and social behavior were all established during this remarkable period in Earth's history. The creatures that pioneered complex vision in these ancient seas had accomplished something unprecedented. They had not just evolved new sensory capabilities, they had fundamentally altered the trajectory of evolution itself. The world they created through their visual innovations would continue to influence the development of life for hundreds of millions of years to come. The visual systems that emerged from this period would continue to evolve and diversify, eventually giving rise to all the sophisticated optical instruments that allow modern animals to navigate their world with precision and grace. But the fundamental principles established by these early visual pioneers would remain constant, providing the foundation for every subsequent advance in animal sensory capability and cognitive complexity. The story of early vision is ultimately a story about the power of sensory innovation to transform entire worlds. When simple light detection evolved into complex image formation, it didn't just create new opportunities for individual organisms, it created new possibilities for life itself, opening up evolutionary pathways that had never existed before, and establishing the foundation for all the remarkable developments in animal intelligence and consciousness that would follow. Animal intelligence and consciousness that would follow. The legacy of those early visual pioneers extends far beyond their immediate success in ancient seas. As we move through the later Paleozoic era, the innovations they established would continue to drive evolutionary change in ways that fundamentally altered the trajectory of life on our planet. The visual systems that had emerged from Cambrian and Ordovician seas were about to face new challenges and opportunities that would push them to even greater levels of sophistication. By the Silurian period, roughly 440 million years ago, marine ecosystems had stabilized into complex networks of interdependent species. But this stability was deceptive. Beneath the surface of these apparently settled communities, evolutionary pressures were building toward another major transformation. The visual innovations that had driven the great diversifications of earlier periods were about to encounter an entirely new set of environmental challenges. One of the most significant of these challenges came from changes in ocean chemistry itself. The increased biological activity driven by visual predators had begun to alter the fundamental chemistry of seawater. Oxygen levels were fluctuating more dramatically than they had in previous geological periods. Nutrient distributions were becoming more complex and unpredictable. The stable chemical environment that had characterized earlier oceans was giving way to more dynamic and variable conditions. These chemical changes created new selective pressures that favored organisms with more flexible and adaptable sensory systems. Simple, specialized visual organs that worked well under constant conditions were less effective in environments where light conditions, water clarity, and chemical composition could change rapidly. The response to these challenges was remarkable. Many marine creatures began evolving what paleontologists call modular visual systems, compound eyes where different regions could be optimized for different environmental conditions. Some areas of these eyes were adapted for high light conditions, others for low light environments. Still others were specialized for detecting specific wavelengths of light that penetrated water under different chemical conditions. This modular approach to vision represented a major advance in optical engineering. Instead of having to choose between different visual strategies, these creatures could essentially switch between multiple optical modes depending on environmental conditions. The neural processing requirements for coordinating these complex visual systems were enormous, but the survival advantages they provided made the investment worthwhile. The fossil record from this period shows clear evidence of these sophisticated visual adaptations. Some trilobite species developed eyes with distinct regional specializations that can still be observed in fossilized specimens. Different areas of the same compound eye show different lens arrangements, different optical properties, and different orientations, all optimized for specific visual tasks. But perhaps most remarkably, some creatures began evolving what can only be described as backup visual systems. These organisms maintained their primary compound eyes for normal vision, but also developed secondary optical organs that could function under extreme conditions. Some had simple light sensors that could detect basic illumination changes when their main eyes were damaged or compromised. Others evolved specialized organs that could detect bioluminescence or other forms of biological light production. The evolution of backup sensory systems represents a major advance in biological redundancy and reliability. These creatures were essentially building fail-safe mechanisms into their sensory apparatus. ensuring that they could continue to function even if their primary visual systems were compromised. This kind of sophisticated system design required neural architectures of unprecedented complexity. The brains that controlled these multimodal visual systems had to be capable of integrating information from multiple sources, switching between different sensory modes, and maintaining coherent behavioral responses, even when primary sensory inputs were disrupted. Modern neuroscience research has shown that many of the principles underlying these ancient multimodal sensory systems are still used by contemporary animals. The basic strategies for integrating information from multiple sensory sources, for maintaining sensory redundancy, and for adapting to changing environmental conditions, all have their origins in these early visual innovations. The success of these adaptive visual systems had profound implications for ecosystem stability and resilience. Communities dominated by organisms with flexible, adaptable sensory capabilities were better able to withstand environmental perturbations and recover from disturbances. This created more robust and sustainable ecological networks that could persist through periods of environmental change. But the most dramatic consequence of these visual innovations was their role in enabling the next major transition in the history of life, the colonization of terrestrial environments. The sophisticated sensory systems that had evolved in marine environments were about to be tested in the radically different conditions found on land. The transition from water to land presented visual systems with challenges that had never been encountered before. Air has completely different optical properties than water. Light behaves differently, colors appear different, and the three-dimensional structure of terrestrial environments is far more complex than most aquatic habitats. Successfully navigating these challenges required modifications to existing visual systems that were both subtle and profound. The compound eyes that worked so well underwater needed to be recalibrated for the different refractive properties of air. Camera eyes required adjustments to their focusing mechanisms to account for the changed optical environment. The earliest terrestrial arthropods show clear evidence of these visual adaptations. Their eye structures are modified in ways that improve performance in air while maintaining some capability for underwater vision. This suggests that the transition to terrestrial life was gradual, with early colonizers spending time in both aquatic and terrestrial environments. Some of the most remarkable examples of these transitional visual systems come from early terrestrial scorpions and primitive insects. These creatures evolved eyes that could function effectively in both water and air, allowing them to exploit resources in intertidal zones and marginal terrestrial habitats. The neural processing challenges associated with these dual environment visual systems were immense. The same optical information had to be interpreted differently depending on whether the animal was in water or air. This required sophisticated neural circuits that could adjust their processing algorithms based on environmental context. The development of these context-sensitive visual processing systems represents one of the most advanced forms of neural computation ever evolved. The fact that creatures with relatively simple nervous systems could accomplish this kind of sophisticated information processing demonstrates just how powerful evolutionary pressure can be in driving innovation. The success of early terrestrial visual systems established the foundation for all subsequent evolution of land-based ecosystems. The arthropods that first learned to see clearly on land would eventually give rise to the complex terrestrial food webs that characterize modern ecosystems. But the transition to land also created new opportunities for visual communication and social behavior. The three-dimensional complexity of terrestrial environments provided far more opportunities for visual signaling than had been available in aquatic habitats. Early terrestrial arthropods could use elevated positions, complex backgrounds, and varied lighting conditions to create sophisticated visual displays. The evolution of terrestrial visual communication systems had profound implications for the development of complex social behaviors. For the first time, organisms could use the three-dimensional structure of their environment to create complex visual signals that could be seen from great distances and could convey detailed information about species identity, reproductive status, and territorial claims. Some of the earliest evidence for sophisticated terrestrial visual communication comes from trace fossils showing complex behavioral patterns that could only have been coordinated through visual signaling. Certain trackway patterns suggest that early terrestrial arthropods were engaging in coordinated group movements, territorial displays, and even primitive courtship behaviors. The cognitive requirements for these complex social behaviors pushed early terrestrial organisms toward greater neural complexity and more sophisticated behavioral repertoires. The brains that emerged from this evolutionary pressure were not just larger than their aquatic predecessors, they were qualitatively different, capable of processing complex social and spatial information in ways that had never existed before. Meanwhile, back in marine environments, the visual arms race was continuing to drive innovation at an unprecedented pace. The Middle Paleozoic saw the evolution of some of the most sophisticated visual predators in Earth's history. Giant cephalopods with camera eyes rivaling those of modern squid dominated the open ocean. Massive arthropods with compound eyes containing thousands of individual lenses patrolled the seafloor. These apex visual predators had profound effects on marine ecosystem structure and function. Their presence created intense selection pressure for improved defensive strategies among prey species. The result was an escalating arms race that drove rapid innovation in both offensive and defensive capabilities. Some prey species evolved remarkably sophisticated camouflage systems that could fool even the most advanced visual predators. Others developed warning coloration strategies that advertised their toxicity or unpalatability through bright, conspicuous patterns that predators learned to avoid. Perhaps most remarkably, some prey species evolved their own advanced visual systems, specifically optimized for predator detection. These anti-predator eyes were often quite different from hunting eyes, designed to detect subtle changes in light patterns or movements that might indicate the presence of a visual predator. The coevolution of predator and prey visual systems during this period created feedback loops that accelerated innovation on both sides of the relationship. As predators developed more sophisticated hunting strategies, prey evolved more effective evasion techniques. As prey became harder to detect and capture, predators evolved even more advanced sensory capabilities. This evolutionary arms race had cascading effects throughout marine ecosystems. The increased sophistication of predator-prey interactions led to more complex food web structures, more efficient energy transfer, and greater overall ecosystem productivity. The chemical signatures of these changes are preserved in rock formations from around the world. Isotope ratios in Middle Paleozoic limestone show clear evidence of increasingly complex biological processes and more sophisticated ecological interactions. Perhaps most significantly, this period saw the emergence of what paleontologists call ecological specialists, organisms that evolved highly specific visual adaptations for particular ecological niches. Some predators specialized in hunting in specific depth zones, developing visual systems optimized for the light conditions found at those depths. Others evolved eyes adapted for hunting particular types of prey, with optical properties tuned to detect the specific visual signatures of their preferred targets. This ecological specialization led to an explosion of diversity as different species carved out increasingly narrow niches within marine ecosystems. The result was a level of biological diversity and ecological complexity that had never been achieved before. The success of visual specialization also had important implications for ecosystem stability. Communities with many specialized visual predators were more resilient to disturbances because the loss of any single species could be compensated for by others with similar but not identical ecological roles. By the late Paleozoic, marine ecosystems had achieved a level of visual sophistication that would not be surpassed until much later in evolutionary history. The compound eyes of arthropods had reached the theoretical limits of their optical performance. Camera eyes had evolved complex focusing mechanisms and sophisticated retinal structures. Even simple eye spots had been refined to remarkable levels of sensitivity and precision. But perhaps the most important legacy of this period was not the sophistication of individual visual systems, but the establishment of the fundamental principles that would guide all subsequent evolution of complex sensory capabilities. The basic strategies for processing visual information, for coordinating sensory and motor systems, and for using vision to guide complex behaviors were all established during this remarkable period in Earth's history. The neural architectures that emerged to support these sophisticated visual systems provided the foundation for all subsequent advances in animal intelligence and consciousness. The cognitive capabilities required to process complex visual information, to make rapid decisions based on sensory input, and to coordinate sophisticated behaviors established the basic framework for all higher-order mental processes. Modern neuroscience research has revealed remarkable similarities between the visual processing strategies used by contemporary animals and those that can be inferred from the fossil record of their ancient relatives. This suggests that the fundamental principles of visual perception and cognition were established very early in the evolution of complex nervous systems. The global impact of these early visual innovations extended far beyond individual species' success. The sophisticated visual systems that evolved during the Paleozoic era transformed the entire biosphere, creating new forms of ecological interaction, new patterns of energy flow, and new levels of biological complexity. The ecosystems that emerged from this period of rapid visual evolution were characterized by intricate networks of predator-prey relationships, complex food webs, and sophisticated patterns of resource use. These biological communities were more diverse, more productive, and more resilient than anything that had existed before. But perhaps most importantly, the visual innovations of the Paleozoic era established the foundation for all subsequent evolution of complex life. The sensory capabilities, neural architectures, and behavioral strategies that emerged during this period would continue to influence the development of life for hundreds of millions of years to come. The creatures that pioneered complex vision in ancient seas had accomplished something truly unprecedented. They had not just evolved new ways of sensing their environment, they had fundamentally altered the nature of life itself. The visual systems they developed opened up entirely new possibilities for biological complexity, intelligence, and consciousness. As we examine the remarkable fossil record from this period, what becomes clear is that the evolution of complex vision was far more than just another sensory innovation. It was a transformative event that accelerated the pace of evolution itself, created new forms of ecological organization, and established the foundation for all the sophisticated cognitive abilities that would eventually emerge in the animal kingdom. The story of early vision is ultimately the story of life discovering its own potential. When the first compound eyes opened in Cambrian seas, they initiated a process of discovery and innovation that continues today. Every modern animal that uses vision to navigate its world, to find food, to avoid predators, or to communicate with others, is participating in an evolutionary experiment that began over 500 million years ago. The visual pioneers of ancient seas didn't just learn to see the world around them. They learned to see possibilities that had never existed before, to imagine futures that could be achieved through evolutionary change, and to transform those visions into biological reality. Their legacy lives on in every eye that sees, every brain that processes visual information, and every behavior that depends on the remarkable gift of sight. The profound transformations we've witnessed throughout the Paleozoic era represent just the opening chapters of vision's revolutionary impact on life. But as we move deeper into Earth's history, we encounter a period that would test these sophisticated visual systems in ways their creators could never have anticipated. The late Paleozoic brought with it environmental challenges that would push the boundaries of biological innovation to their absolute limits. Around 375 million years ago, during what geologists call the late Devonian extinction event, marine ecosystems faced a crisis that threatened to undo millions of years of evolutionary progress. Ocean oxygen levels plummeted dramatically. Sea surface temperatures fluctuated wildly. The chemical composition of seawater changed in ways that made traditional hunting and survival strategies increasingly ineffective. For creatures that had become dependent on sophisticated visual systems, these changes posed existential challenges. Many of the optical innovations that had proven so successful in stable marine environments suddenly became liabilities in the chaotic conditions of the late Devonian crisis. The fossil record from this period tells a sobering story of adaptation under extreme pressure. Many of the most specialized visual predators, creatures that had invested enormous amounts of energy in highly refined optical systems, simply couldn't adapt quickly enough to the changing conditions. Their fossilized remains mark the end of evolutionary lineages that had dominated marine ecosystems for tens of millions of years. But within this apparent catastrophe lay the seeds of even greater innovation. The environmental pressures that destroyed some visual systems also created opportunities for entirely new approaches to the challenge of sight. Creatures that had maintained more flexible, adaptable visual capabilities found themselves with access to ecological niches that had been monopolized by their more specialized competitors. The recovery from the late Devonian extinction reveals one of the most remarkable examples of evolutionary resilience in the entire fossil record. Within just a few million years of the crisis, marine ecosystems had not only recovered their previous levels of diversity, they had exceeded them. The visual systems that emerged from this period were more sophisticated, more adaptable, and more efficient than anything that had existed before. One of the most significant innovations to emerge from this period was the development of what paleontologists call adaptive visual processing. Instead of having fixed optical systems optimized for specific conditions, many creatures evolved visual systems that could modify their performance in real time based on environmental feedback. These adaptive systems represented a quantum leap in biological sophistication. They required neural circuits that could monitor environmental conditions, assess the performance of existing visual systems, and make real-time adjustments to optimize optical function. The computational requirements for this kind of dynamic system management were staggering, but the survival advantages they provided made the investment worthwhile. Modern analysis of fossilized structures from this period reveals remarkable evidence of these adaptive capabilities. Some compound eyes show clear signs of having been able to adjust the sensitivity of individual lenses based on local light conditions. Others appear to have been capable of modifying their focus dynamically, essentially creating biological autofocus systems that could track moving targets with unprecedented precision. The success of these adaptive visual systems had profound implications for predator-prey dynamics. For the first time in evolutionary history, visual predators could maintain peak hunting efficiency across a wide range of environmental conditions. This gave them enormous advantages over prey species that relied on environmental variability to reduce predation pressure. The response from prey species was equally remarkable. Many evolved what can only be described as counter-adaptive strategies, behavioral and morphological innovations specifically designed to exploit the limitations of adaptive visual systems. Some developed rapid color-changing abilities that could confuse predators using dynamic visual tracking. Others evolved erratic movement patterns that were designed to overload the processing capacity of adaptive visual systems. This escalating arms race between adaptive predator vision and counter-adaptive prey strategies drove innovation at an unprecedented pace. The late Paleozoic saw an explosion of new visual capabilities, new defensive strategies, and new forms of sensory-motor coordination that established many of the basic principles still used by modern animals. Perhaps most remarkably, this period witnessed the evolution of what paleontologists call metacognitive visual processing. Some creatures develop the ability to monitor and evaluate their own visual performance, essentially becoming conscious of their own perceptual capabilities and limitations. The evidence for this sophisticated cognitive ability comes from trace fossils showing complex decision-making patterns that can only be explained by self-awareness of visual capabilities. Certain trackways show clear evidence of animals adjusting their hunting strategies based on their assessment of their own visual performance under specific conditions. This kind of metacognitive awareness represents one of the most advanced forms of animal intelligence ever documented in the fossil record. The neural architectures required to support self-monitoring of perceptual systems are incredibly complex, involving sophisticated feedback loops between sensory processing areas and higher-order cognitive centers. The development of metacognitive visual processing had cascading effects throughout late Paleozoic ecosystems. Animals that could accurately assess their own perceptual limitations were better able to make strategic decisions about when to hunt, when to hide, and when to engage in risky behaviors like mating displays or territorial contests. These enhanced decision-making capabilities led to more sophisticated social behaviors and more complex ecological relationships. Communities of metacognitively aware animals could coordinate their activities more effectively, avoid wasteful conflicts more consistently, and exploit resources more efficiently than their less self-aware competitors. The fossil record from this period also reveals the emergence of what can only be described as visual culture. Some species show evidence of maintaining consistent visual signaling traditions across multiple generations, with specific display patterns being passed down from parents to offspring through social learning. The ability to maintain cultural traditions requires sophisticated memory systems, advanced social learning capabilities, and complex communication networks. The fact that visual creatures were developing these capabilities over 350 million years ago demonstrates just how advanced late Paleozoic cognitive systems had become. But perhaps the most significant development of this period was the emergence of what paleontologists call ecological vision. Instead of simply using their eyes to hunt individual prey or avoid individual predators, many creatures began using vision to monitor and respond to ecosystem-level patterns and processes. Some predators evolved the ability to track population dynamics of their prey species, adjusting their hunting strategies based on long-term trends rather than immediate opportunities. Others developed capabilities for monitoring environmental health, using visual cues to assess the condition of their habitats and make strategic decisions about territory selection and resource allocation. This ecosystem-level visual awareness represents one of the most sophisticated forms of environmental perception ever evolved. It requires the ability to integrate visual information across multiple spatial and temporal scales, to recognize complex patterns in ecological data, and to make predictions about future environmental conditions based on current observations. The creatures that developed ecological vision gained enormous advantages in the increasingly complex and variable environments of the late Paleozoic. They could anticipate environmental changes before they became critical, identify new opportunities before their competitors, and avoid ecological traps that caught less perceptually sophisticated species. The success of ecological vision also had important implications for ecosystem stability and resilience. Animals that could monitor and respond to ecosystem-level patterns served as early warning systems for environmental changes, helping to maintain the health and stability of their communities. Modern ecological research has revealed that many contemporary animals use similar ecosystem monitoring strategies, suggesting that the basic principles of ecological vision were established during the late Paleozoic and have remained essentially unchanged for over 300 million years. The global impact of these late Paleozoic visual innovations extended far beyond individual ecosystem effects. As creatures with sophisticated visual capabilities spread throughout the world's oceans, they created new forms of biological connectivity that linked distant marine communities through shared visual strategies and coordinated behaviors. Some species developed the ability to navigate across vast oceanic distances using visual landmarks and celestial cues. Others evolved sophisticated communication systems that allowed them to coordinate their activities with distant populations. These innovations created the first truly global biological networks, linking marine ecosystems across entire ocean basins. The development of global biological connectivity had profound implications for the evolution and spread of new innovations. Successful adaptations could now spread rapidly between distant populations, accelerating the pace of evolutionary change and increasing the likelihood that beneficial mutations would be preserved and amplified. But perhaps most importantly, the late Paleozoic established the foundation for one of the most significant transitions in the history of life: the full colonization of terrestrial environments. The sophisticated visual systems that had evolved in marine habitats were about to be tested in the radically different conditions found on land. The transition from marine to terrestrial vision required modifications that were both subtle and profound. The optical properties of air are completely different from those of water. The three-dimensional complexity of terrestrial environments far exceeds that of most aquatic habitats. The availability of visual landmarks and navigation cues is dramatically different between marine and terrestrial settings. Successfully adapting to these challenges required evolutionary innovations that pushed the boundaries of what biological optical systems could achieve. Some creatures developed hybrid visual systems that could function effectively in both aquatic and terrestrial environments. Others evolved specialized terrestrial optical adaptations that were completely different from their marine ancestors. The most successful terrestrial visual innovations combined the best features of both compound and camera eye designs. These hybrid systems could provide the wide-angle surveillance capabilities of compound eyes while maintaining the high-resolution detail detection of camera eyes. The neural processing requirements for these hybrid visual systems were enormous, but the advantages they provided in complex terrestrial environments made the investment worthwhile. Creatures with hybrid vision could simultaneously monitor large areas for threats while maintaining the ability to examine small objects and details with high precision. The success of hybrid visual systems established many of the basic principles that would guide the evolution of terrestrial vision for hundreds of millions of years to come. The same fundamental strategies for combining wide-angle surveillance with high-resolution detail work are still used by many modern terrestrial animals. But the transition to terrestrial vision also created entirely new opportunities for visual communication and social behavior. The complex three-dimensional structure of terrestrial environments provided unprecedented possibilities for visual signaling and display. Early terrestrial arthropods evolved elaborate visual display systems that took full advantage of the complex lighting conditions and varied backgrounds found in terrestrial habitats. Some developed the ability to create sophisticated visual patterns by positioning themselves against specific backgrounds. Others evolved specialized body structures that could manipulate light and shadow to create complex visual signals. The cognitive requirements for these sophisticated visual communication systems were immense. Animals had to be able to assess lighting conditions, choose appropriate backgrounds, coordinate their movements with environmental features, and monitor the responses of their intended audience. This required neural architectures of unprecedented complexity and sophistication. The development of complex terrestrial visual communication had profound implications for the evolution of animal societies. For the first time, organisms could use the three-dimensional structure of their environment to create visual signals that could convey detailed information about individual identity, social status, reproductive condition, and territorial claims. Some early terrestrial communities show clear evidence of having developed sophisticated social hierarchies based on visual displays and recognition systems. Certain fossil assemblages preserve evidence of territorial boundaries, mating grounds, and social gathering areas that could only have been maintained through complex visual communication networks. The establishment of visually mediated social systems on land created new evolutionary pressures that drove rapid innovation in cognitive capabilities. Animals that could successfully navigate complex social environments gained enormous advantages in terms of resource access, mating opportunities, and protection from predators. The neural architectures that evolved to support these complex social behaviors provided the foundation for many of the cognitive capabilities that would eventually characterize advanced animal intelligence. The ability to recognize individuals, remember social relationships, and coordinate complex group behaviors all have their origins in the visual innovations of early terrestrial communities. By the end of the Paleozoic era, vision had become far more than just a sensory modality. It had evolved into a comprehensive system for environmental monitoring, social coordination, and cognitive processing that influenced virtually every aspect of animal behavior and ecology. The visual systems that emerged from this remarkable period of evolutionary innovation were not just more sophisticated than their predecessors, they were qualitatively different. They represented a new level of biological organization where sensory perception, cognitive processing, and behavioral coordination were integrated into unified systems of unprecedented complexity and capability. The creatures that pioneered these advanced visual systems had essentially created the foundation for all subsequent evolution of complex animal intelligence. The basic principles of visual perception, spatial reasoning, social cognition, and environmental monitoring that they established would continue to guide evolutionary innovation for hundreds of millions of years to come. Modern neuroscience research has revealed that many of the fundamental strategies used by contemporary animals for processing visual information and coordinating complex behaviors can be traced directly back to innovations that first appeared during the Paleozoic era. This remarkable conservation of basic principles demonstrates just how successful these early visual pioneers were in discovering optimal solutions to the challenges of perception and cognition. The global impact of Paleozoic visual innovations extended far beyond their immediate effects on individual species and ecosystems. These innovations fundamentally altered the trajectory of evolution itself, creating new possibilities for biological complexity and establishing the foundation for all subsequent advances in animal intelligence and consciousness. The sophisticated visual systems that evolved during this period created feedback loops between perception, cognition, and behavior that accelerated evolutionary innovation across all aspects of animal biology. The same neural architectures that processed visual information also supported advances in memory, learning, decision-making, and social coordination. As we examine the remarkable fossil record from the late Paleozoic, what becomes clear is that the evolution of complex vision had grown into something far more significant than anyone could have anticipated. What began as simple light detection had evolved into comprehensive systems for environmental monitoring, social coordination, and cognitive processing that established many of the fundamental principles still governing animal behavior today. The visual revolution that started with the first compound eyes of trilobites had culminated in the creation of biological information processing systems of unprecedented sophistication. These systems could monitor complex environmental patterns, coordinate sophisticated social behaviors, and support cognitive capabilities that approach the threshold of true consciousness and self-awareness. The creatures that achieved these remarkable capabilities were essentially creating the blueprint for all subsequent evolution of complex animal intelligence. The visual innovations they developed would continue to influence the development of life for hundreds of millions of years, providing the foundation for every subsequent advance in animal cognition and consciousness. The legacy of Paleozoic visual innovation was about to face its ultimate test. As we move into the Permian period, roughly 299 million years ago, the sophisticated visual ecosystems that had taken hundreds of millions of years to develop were approaching a catastrophe that would challenge every adaptation, every innovation and every survival strategy that evolution had produced. The Great Permian Extinction, occurring around 252 million years ago, represents the most severe extinction event in Earth's history. Over 90% of marine species vanished from the fossil record within a geological instant. The complex visual ecosystems that had dominated ancient seas for nearly 300 million years were decimated. Yet from this apparent ending would emerge some of the most remarkable innovations in the entire history of vision. But before we examine how sight survived this planetary catastrophe, we need to understand just how sophisticated these doomed ecosystems had become. The latest Permian seas contained visual predators and prey locked in evolutionary arms races of staggering complexity. Some marine arthropods had evolved compound eyes containing over 15,000 individual lenses, creating optical instruments that could detect movement across vast distances while simultaneously tracking multiple targets with microscopic precision. These were not simple hunting tools. They were biological computers capable of processing visual information at rates that challenged the limits of neural processing. Recent analysis of fossilized neural pathways in late Permian arthropods suggests that some species were dedicating nearly 70% of their nervous system capacity to visual processing and the behavioral coordination required to use that information effectively. The prey species they hunted had evolved equally sophisticated countermeasures. Some developed chameleonic abilities that could shift coloration faster than their predators could adjust their visual tracking systems. Others evolved what paleontologists call quantum camouflage, body patterns that exploited the specific wavelength sensitivities of their predators' visual systems to create near-perfect invisibility under certain lighting conditions. Perhaps most remarkably, some late Permian creatures had begun evolving what can only be described as predictive vision. These organisms could analyze the movement patterns of their prey or predators and calculate probable future positions, allowing them to intercept moving targets or avoid pursuing threats with uncanny accuracy. The neural architectures required for predictive visual processing represent some of the most advanced biological computation ever documented in the fossil record. These systems had to integrate current visual information with stored movement pattern data, perform complex spatial calculations, and coordinate precise motor responses, all in real time. The fact that creatures with relatively simple brains could accomplish this level of computational sophistication demonstrates just how powerful evolutionary pressure can be in driving innovation. But these magnificent visual ecosystems were built on foundations that were becoming increasingly unstable. The massive volcanic eruptions that triggered the Permian extinction released enormous quantities of carbon dioxide, hydrogen sulfide, and other gases that fundamentally altered ocean chemistry. Water that had been crystal clear for millions of years became cloudy, acidic, and increasingly hostile to the sophisticated optical systems that had evolved to exploit its transparency. The extinction itself unfolded with terrifying speed. Geological evidence suggests that the most severe phase lasted only 60,000 years, a geological instant that allowed virtually no time for evolutionary adaptation. The visual predators that had ruled ancient seas for hundreds of millions of years found themselves suddenly blind in waters that no longer transmitted light effectively. Yet within this catastrophe lay extraordinary opportunities. As the dominant visual predators disappeared, ecological niches that had been monopolized for millions of years suddenly became available. The few creatures that survived the extinction possessed visual systems robust enough to function under the degraded conditions of post-extinction oceans. These survivors shared certain characteristics that had proven crucial for navigating the chaos of the extinction event. Many had maintained relatively simple, flexible visual systems rather than the highly specialized optical instruments that had dominated late Permian ecosystems. Others had evolved redundant sensory capabilities that allowed them to compensate when their primary visual systems were compromised. Most importantly, the survivors possessed neural architectures that could rapidly adapt to changing environmental conditions. While their more specialized competitors had invested everything in optimizing performance under stable conditions, these resilient creatures had maintained the flexibility to modify their visual processing strategies as circumstances required. The recovery from the Great Permian extinction reveals one of the most remarkable examples of evolutionary resilience in Earth's history. Within just 5 million years of the extinction event, marine ecosystems had not only recovered their previous levels of diversity, they had begun exploring entirely new approaches to the challenge of vision. The Triassic period, beginning around 252 million years ago, witnessed an explosion of visual innovation that rivaled the great diversifications of the Cambrian and Ordovician periods. But this new wave of innovation was fundamentally different from what had come before. Instead of simply refining existing visual strategies, Triassic creatures began experimenting with completely novel approaches to sight. One of the most significant innovations to emerge from this period was the development of hybrid sensory systems that combined vision with other sensory modalities in unprecedented ways. Some creatures evolved eyes that could simultaneously detect light and electromagnetic fields, creating unified sensory systems that could track both visible and invisible environmental features. Others developed visual systems that were integrated with chemical sensing capabilities, allowing them to see and smell simultaneously. These multimodal sensory systems provided enormous advantages in the variable and unpredictable environments of the early Triassic, where traditional visual strategies often failed due to changing water chemistry and light conditions. The neural processing requirements for these hybrid sensory systems were staggering, but they represented a fundamental advance in biological information processing. For the first time in evolutionary history, single organisms could integrate multiple types of environmental information into unified perceptual experiences that provided far more complete pictures of their surroundings than any single sensory modality could achieve. Modern neuroscience research has revealed that many of the basic principles underlying these ancient multimodal sensory systems are still used by contemporary animals. The strategies for integrating visual, chemical, and electromagnetic information that evolved during the Triassic recovery established many of the fundamental principles that continue to guide sensory system design today. But perhaps the most remarkable innovation of this period was the emergence of what paleontologists call collaborative vision. Some Triassic creatures evolved the ability to share visual information with other members of their species, creating collective sensory networks that far exceeded the capabilities of any individual organism. The evidence for collaborative vision comes from fossil assemblages showing complex coordination patterns that could only have been achieved through shared sensory information. Certain trackway systems preserve evidence of group hunting strategies that required multiple individuals to coordinate their visual tracking of prey across vast distances and complex terrain. The cognitive requirements for collaborative vision were enormous. Individual organisms had to be able to communicate detailed visual information to others, integrate received information with their own sensory input, and coordinate their behaviors with other group members in real time. This required neural architectures of unprecedented complexity and sophistication. The success of collaborative visual systems had profound implications for ecosystem organization and function. Groups of organisms with shared sensory capabilities could monitor much larger areas than individual creatures, detect threats and opportunities more quickly, and coordinate responses more effectively than solitary hunters or defenders. These collaborative sensory networks also established many of the basic principles that would eventually give rise to complex animal societies. The ability to share information, coordinate activities, and make collective decisions all have their origins in the collaborative visual systems that emerged during the Triassic recovery. The Triassic period also witnessed the emergence of vertebrate vision as a major evolutionary force. While arthropods had dominated visual innovation throughout the Paleozoic era, the post-extinction recovery created opportunities for vertebrates to develop their own sophisticated optical systems. Early Triassic vertebrates evolved camera eyes that incorporated many of the innovations that had been pioneered by arthropod compound eyes. Some developed adjustable pupils that could rapidly adapt to changing light conditions. Others evolved specialized retinal regions that could simultaneously optimize for different visual tasks. Perhaps most significantly, some early vertebrates began developing what would eventually become the foundation for all advanced vertebrate vision. Sophisticated neural processing systems that could extract complex information from relatively simple optical inputs. The vertebrate approach to vision was fundamentally different from the arthropod strategy. Instead of using thousands of individual lenses to sample the environment, vertebrates used single, high-quality lenses combined with advanced neural processing to extract maximum information from their visual input. This neural approach to vision proved incredibly successful. While it required more sophisticated brain structures than the arthropod strategy, it also provided much greater flexibility and adaptability. Vertebrate visual systems could be rapidly modified through changes in neural processing without requiring physical modifications to optical structures. The success of vertebrate vision during the Triassic recovery established the foundation for all subsequent evolution of complex cognition and consciousness. The neural architectures that evolved to support sophisticated visual processing also provided the framework for advanced memory, learning, decision-making, and abstract thinking. By the Middle Triassic, roughly 240 million years ago, marine ecosystems had achieved levels of visual sophistication that exceeded anything that had existed before the Great Extinction. The innovations that emerged during the recovery period had not simply restored previous capabilities, they had fundamentally advanced the state of biological visual processing. The creatures that inhabited these recovered ecosystems possessed sensory capabilities that would have seemed almost magical to their Paleozoic predecessors. They could see across multiple sensory modalities, share information with other members of their species, and coordinate complex behaviors through sophisticated communication networks. But perhaps most importantly, they had developed the cognitive foundations that would eventually support the evolution of true consciousness and self-awareness. The neural architectures that evolved to support advanced visual processing during the Triassic recovery established many of the basic principles that continue to govern animal cognition today. The global impact of Triassic visual innovations extended far beyond marine ecosystems. As sophisticated visual systems spread throughout the recovering biosphere, they began influencing the evolution of terrestrial life in ways that would have profound implications for the future development of complex ecosystems. Some of the most remarkable terrestrial visual innovations of this period came from early archosaurs, the group that would eventually give rise to dinosaurs, crocodiles, and birds. These creatures evolved visual systems that combined the best features of both compound and camera eyes, creating hybrid optical instruments of unprecedented capability. Early archosaur vision was characterized by remarkable versatility and adaptability. Some species could adjust their visual processing strategies in real time based on environmental conditions. Others developed specialized visual modes for different activities, like hunting, territorial defense, and social communication. The success of archosaur visual systems had profound implications for terrestrial ecosystem development. These creatures became the dominant terrestrial predators of their time, using their sophisticated sight to coordinate complex hunting strategies and maintain elaborate social hierarchies. The social behaviors that emerged among early archosaurs were supported by visual communication systems of remarkable complexity. Some species developed elaborate display structures and behavioral repertoires that could convey detailed information about individual identity, social status, reproductive condition, and territorial claims. The cognitive requirements for these sophisticated social systems pushed early archosaurs toward greater neural complexity and more advanced behavioral capabilities. The brains that evolved to support complex social coordination also provided the foundation for many other cognitive advances, including enhanced memory, learning, and problem-solving abilities. By the late Triassic, roughly 210 million years ago, both marine and terrestrial ecosystems had achieved levels of visual sophistication that established the foundation for all subsequent evolution of complex animal intelligence. The innovations that emerged during the post-extinction recovery had fundamentally advanced the capabilities of biological information processing systems. The visual systems that characterized late Triassic ecosystems were not just more sophisticated than their predecessors, they were qualitatively different. They represented a new level of biological organization where sensory perception, cognitive processing, and behavioral coordination were integrated into unified systems of unprecedented complexity and capability. These advanced visual systems also established many of the basic principles that would guide the evolution of dinosaur intelligence and behavior. The same neural architectures that supported sophisticated visual processing in early archosaurs would eventually give rise to the complex cognitive capabilities that characterized many dinosaur species. The success of Triassic visual innovations also created the foundation for one of the most significant developments in the history of life: the evolution of flight. The sophisticated spatial processing capabilities that had evolved to support terrestrial visual navigation would prove crucial for the three-dimensional challenges of aerial locomotion. Early pterosaurs, the first vertebrates to achieve powered flight, possessed visual systems of extraordinary sophistication. They could process complex three-dimensional spatial information in real time, coordinate precise motor responses during rapid aerial maneuvers, and navigate accurately across vast distances using visual landmarks and celestial cues. The neural processing requirements for flight-capable vision were enormous, but the advantages provided by aerial locomotion made the investment worthwhile. Flying creatures could access resources unavailable to terrestrial organisms, escape from ground-based predators, and exploit ecological niches that had never been occupied before. The success of aerial visual systems established many of the basic principles that would eventually guide the evolution of bird and bat vision. The same fundamental strategies for processing three-dimensional spatial information and coordinating complex motor responses are still used by modern flying vertebrates. But perhaps the most significant legacy of Triassic visual innovation was its role in establishing the foundation for advanced animal consciousness. The sophisticated neural architectures that evolved to support complex visual processing also provided the framework for self-awareness, abstract thinking, and other higher-order cognitive capabilities. The creatures that achieved these remarkable cognitive advances were essentially creating the blueprint for all subsequent evolution of animal intelligence and consciousness. The visual innovations they developed established many of the fundamental principles that continue to guide the development of complex nervous systems today. As we examine the extraordinary fossil record from the Triassic recovery, what becomes clear is that the Great Permian extinction, despite its devastating immediate effects, ultimately accelerated rather than hindered the evolution of sophisticated visual systems. The catastrophe had eliminated the highly specialized but inflexible visual predators of the late Paleozoic, creating opportunities for more adaptable and resilient approaches to sight. The visual innovations that emerged from this period of recovery and experimentation established the foundation for all subsequent evolution of complex animal cognition and behavior. From the compound eyes of insects to the camera eyes of vertebrates, from the echolocation systems of bats to the magnetic sensing capabilities of migrating birds, virtually every sophisticated sensory system used by modern animals can trace its origins back to innovations that first appeared during the remarkable recovery that followed Earth's greatest extinction event. The story of vision's survival and transformation through the Permian extinction demonstrates one of the most important principles in evolutionary biology: that apparent endings often represent new beginnings, and that the greatest innovations frequently emerge from the greatest challenges. The sophisticated visual systems that characterize modern ecosystems are the direct descendants of creatures that refuse to let darkness win. that found new ways to see when the old ways failed, and that transformed catastrophe into opportunity through the power of evolutionary innovation. Innovation. The creatures that emerged from the Permian catastrophe carried with them something unprecedented in the history of life. Their visual systems weren't just tools for survival anymore. They had become instruments of exploration, discovery, and ultimately, understanding. As we move into the Mesozoic era, roughly 252 million years ago, we witness vision evolving beyond mere perception into something approaching true comprehension of the world. The early Mesozoic oceans were unlike anything that had existed before. The extinction had reset the evolutionary clock, but the recovery brought innovations that would have been impossible under the stable conditions of the Paleozoic. Marine reptiles began developing visual systems that could function across multiple environments simultaneously. Some early ichthyosaurs evolved eyes that could process visual information both underwater and at the surface, allowing them to hunt prey that moved between these optical domains. But perhaps most remarkably, these early marine reptiles developed what paleontologists now recognize as the first evidence of visual memory systems sophisticated enough to support complex learning behaviors. Fossil trackways from the early Triassic show hunting patterns that could only be explained by predators that remembered the locations of successful hunts and returned to them repeatedly. This represents a quantum leap in cognitive sophistication. Simple visual tracking requires real-time processing of sensory information. But visual memory-based hunting requires the ability to encode spatial information, store it for extended periods, and recall it accurately when environmental cues suggest it might be useful. The neural architectures required for this kind of cognitive processing were unlike anything that had existed before. The success of memory-enhanced visual hunting had cascading effects throughout early Mesozoic ecosystems. Prey species were forced to develop counter-strategies that went far beyond simple escape responses. Some evolved what can only be described as deceptive behaviors, creating false trails and misleading visual cues designed to confuse predators that relied on memory-based hunting patterns. Others developed nomadic lifestyles that made memory-based predation strategies ineffective. These creatures never remained in the same location long enough for visual predators to establish reliable hunting patterns. The result was an evolutionary arms race between memory and mobility that drove rapid innovation on both sides of the predator-prey relationship. Meanwhile, on land, the archosaurs that would eventually give rise to dinosaurs were developing visual innovations that would transform terrestrial ecosystems forever. Early dinosaur ancestors evolved visual systems with unprecedented resolution and processing speed. Some species developed eyes that could track multiple moving targets simultaneously, while maintaining detailed focus on specific objects of interest. The fossil record reveals that these early archosaurs were engaging in complex social behaviors that required sophisticated visual communication systems. Some species developed elaborate display structures that could create intricate patterns of light and shadow. Others evolved the ability to coordinate their movements in ways that created collective visual displays involving dozens of individuals. These collective displays represent some of the earliest evidence for what behaviorists call emergent intelligence. Individual organisms with relatively simple cognitive capabilities could combine their efforts to create complex, coordinated behaviors that exceeded what any single individual could accomplish alone. The visual coordination required for these group displays pushed early archosaur nervous systems toward greater complexity and integration. By the Middle Triassic, roughly 235 million years ago, some dinosaur lineages had begun developing visual capabilities that approached the theoretical limits of what biological systems could achieve. Certain species evolved eyes with such high resolution that they could detect individual features on objects at distances that exceeded the visual capabilities of most modern animals. But raw resolution was only part of the story. These early dinosaurs also developed neural processing systems that could extract extraordinary amounts of information from their visual input. They could assess the health, age, and emotional state of other individuals through subtle visual cues. They could predict weather patterns by observing cloud formations and atmospheric conditions. They could even navigate across vast distances using visual landmarks and celestial navigation techniques. The cognitive requirements for these sophisticated visual capabilities were enormous. Processing high-resolution visual information requires massive amounts of neural computational power. Integrating that information with memory systems, decision-making processes, and motor coordination systems requires even more. Some early dinosaur species were dedicating up to 80% of their nervous system capacity to visual processing and the cognitive functions that depended on it. This enormous investment in visual processing paid dividends that extended far beyond individual survival. Dinosaurs with sophisticated visual systems could coordinate complex group behaviors, maintain elaborate social hierarchies, and engage in cooperative activities that gave them enormous advantages over their competitors. The success of dinosaur visual innovations had profound effects on global ecosystem structure. These creatures became the dominant terrestrial vertebrates of their time, using their sophisticated sight to exploit ecological niches that had never been fully utilized before. Their visual capabilities allowed them to hunt more efficiently, defend territories more effectively, and coordinate social activities more successfully than any previous terrestrial vertebrates. But the most remarkable aspect of dinosaur visual evolution was its role in driving the development of advanced cognitive capabilities. The neural architectures that evolved to support sophisticated visual processing also provided the foundation for enhanced memory, learning, problem-solving, and even primitive forms of abstract thinking. Some dinosaur species show clear evidence of having been capable of what cognitive scientists call insight learning, the ability to solve novel problems through reasoning rather than trial and error. Trackway evidence suggests that certain species could assess complex environmental challenges and develop innovative solutions without extensive experimentation. Others appear to have been capable of teaching and learning complex behaviors through visual demonstration and imitation. Fossil evidence from some dinosaur nesting sites shows behavioral patterns that could only be maintained through cultural transmission across multiple generations. These cognitive advances had profound implications for dinosaur social organization. Species with advanced learning capabilities could develop and maintain complex cultural traditions. Groups that could coordinate their activities through visual communication could accomplish tasks that were impossible for solitary individuals. The late Triassic period, roughly 210 million years ago, witnessed the emergence of some of the most sophisticated visual systems in Earth's history. Large predatory dinosaurs evolved eyes that combined exceptional resolution with advanced motion detection capabilities. They could spot potential prey across vast distances while simultaneously tracking multiple targets and monitoring their environment for threats. But perhaps most remarkably, some of these apex predators developed what paleontologists call strategic vision, the ability to use visual information to plan complex multi-stage hunting strategies. Instead of simply reacting to immediate visual stimuli, these creatures could assess environmental conditions, predict prey behavior, and coordinate elaborate ambush tactics that unfolded over extended periods. The story of vision's birth in those ancient Cambrian seas isn't just a chapter from Earth's distant past. It's the foundation of everything you see around you right now. Every time you catch a glimpse of movement in your peripheral vision, track a bird across the sky, or recognize a friend's face in a crowd, you're using neural pathways and optical principles that were first developed by trilobites swimming through primordial oceans over 500 million years ago. The evolutionary experiment that began with those first compound eyes didn't just change life on Earth. It created the very possibility of awareness, consciousness, and understanding that makes us human.